So thanks everyone for joining. This is going to be a webinar around how do you do production scale and production grade fine tuning and customization of visual language action models. And to take you to the journey on that, it's going to be two of us on screen and then one person helping us with Q&A. So I want to do a quick intro of who's going to be on screen. So from my side, Julian, I lead the product go-to-market team. Been in the infra space and AI space for over 12 years. You can trust me that I was helping customers figure out how to run Spark on-prem. And so it's been a long journey till the world we are in today. And then I'm joined by who's going to be the star of the show and taking us through all the demo and technical side of things. Omar, you want to do a quick intro on your side?
Sure. Hello, everyone, and welcome. Omar Sharbaji. I am an engineer with the field engineering team here at Anyscale. Over the past couple of years, I've had the opportunity to work with a lot of robotics and autonomous vehicle companies, and VLAs, of course, are an important part of that. Today, I'll be walking you through architecture and code, how to scale VLAs. So I will be showing a notebook and you will be able to follow along as well. Looking forward to engagement. Don't hesitate to ask questions along the way.
Yeah, and then there's going to be someone from Omar's team behind the scenes, Ian, who is going to be helping answer Q&A along the way. So, like I said, use the Q&A functionality. We're going to be doing some ad hoc along the way, but then also saving some time to do more like live Q&A at the end. Okay, so what's in it for today? So pretty much is I kind of saw the sign up registration. There's a few of you that are like robotics engineers. Some of you are maybe coming from a different side of AI. And just to make sure that we're all on the same page around like what VLAs are and kind of how we got here, I'm just gonna do a quick intro. And then from there, Omar is gonna take it to talk about Anyscale as well as go through the demo that he talked about. So give me 6, 7 minutes and then you guys will be on your journey with Omar. So really all I want to highlight is that if you think about physical AI, right, there's many ways to think about the stack. But in some way, a way to think about it is what's been the functionality that's been added over time so that you can really go from problem and executing and building everything around an actual action that a robotic system is going to take. And so really from the beginning, we've kind of started on this world of just enabling vision, right? How do we do object detection? How do we enable robots to see? And that was kind of like the journey that we were on, right? How do we build models? Maybe one model's good at this versus the other one, segmenting, learning how things are in there. But there wasn't really like a lot of understanding beyond looking for a specific item, right? Which is why we had many different models for different objects that need to be recognized. And once LLMs came in, kind of this added a new world of like, hey, what if I could use all this pre-trained knowledge on the world, right? We had these like multimodal models that could like see pictures and then describe the pictures. And so how do we bring that into the world of robotics? And that kind of brought kind of like unlocking cognition next to perception. Images could be described and then it could kind of reason around the things that the system was looking at. And then now, of course, I think a big moment was sort of like when physical intelligence launched the Pi Zero model, which is really that big moment that said, hey, by building these sort of like, you can think of them as foundational models for robotics, these visual language action models, they really think about the process end to end. And so it's like a single system that can go from what do you see to how do you act and do that all as part of a unified way to think about the model. And so it's pretty awesome, kind of like how we've gotten there, but that's kind of meant a lot of things, right? We talked about they had to use a lot of data to do that, and we've kind of built larger architectures on the models. And so what I wanted us to kind of like ground on like where in the robotics workflow and the physical AI workflow are we going to be talking about today? Broadly, you can kind of think of like there is your compute intensive data preparation and model training fine tuning steps that you typically do in something like a on-prem HPC cluster. In this case, we're going to talk about it in the context of the cloud. And then of course, your low latency serving side of things on device. And something that I want to say is that as we've moved towards these more advanced model capabilities, right, you want to get to that fine-tuning model step at the end, but really there's a lot of data preparation that happens along the way. And while there used to be a lot of data preparation that was mostly CPU based, we've started to add more GPU-based steps by using models themselves, whether it's like ones that you're training or off-the-shelf models to do some additional enhancements to your data. And sometimes that may even include using some LLMs, right, to be generating certain descriptions or different features around your data. And then, of course, it's not just images. Many times you're going to have to also process logs alongside and do synchronization and alignment and run also some new GPU steps on that, like embedding generation. And so what happens is that as someone that's working in this space, whether you're a perception engineer, a robotics engineer, an ML engineer, right, you're kind of dealing with this world of not only CPU for data preparation and GPU for fine-tuning, you're kind of using these heterogeneous compute resources end to end along your experimentation journey. And you're having to think about doing things like how do I run batch AI inference to do some data pre-processing? Many of you have kind of started to do at scale. You realize that one of the challenges in making your GPUs run efficiently is like how do I load the data, how do I load the data fast enough into the GPUs? And then, of course, because the data sets and the models have gotten larger, single node compute or like 8 GPUs even is not enough to get this thing across the way. And so that's something that Omar is going to touch on specifically. Now, what I want to highlight before going to into the tech is that Anyscale has customers who've been solving these challenges. One of them is physical intelligence, who is able to empower their engineers to focus and their researchers to focus on model development by abstracting the complexity of doing the data processing. Right? They're analyzing terabytes worth of logs and video, and how do they do this in a way that helps them stay focused on the model development side of things? And one of the things we talked about, right, is there's a lot of GPU steps that need to be used now, not only on the fine tuning, but also on the data preparation. And so then how do you access this like sort of capacity constrained resource right now, which is GPUs? And so being able to do this across clouds. And so currently we support them on their journey using both AWS and GCP. But you could say like, hey, physical intelligence, right? Kind of like they're at the cutting edge because they're the ones that created these like VLAs that a lot of us use as foundation models. But as more robotics organizations and teams start to use this, right, they're running into pretty much the same challenges because you want to build customizations for your own proprietary data sets. And so Bonsai Robotics is an example of this. They had purchased a node that they were running on-prem, but this was leading to some challenges in scaling both the team and the workloads. And so even though it's a small team of like 2 engineers that started growing into more, they were able to use the Anyscale platform to do something very similar and be able to do that end-to-end experimentation loop with the same technology and the same ability to scale infrastructure, just like any large AI lab. And so with that, I have a couple questions for the audience to kind of ground us on where everyone is on their journey. And so the first question to kind of get a glance of like where the audience is at and to kind of tailor things a little bit more, wanted to see how where everyone is on their journey. Awesome. Keep it's really cool to see kind of like the live data and everyone being able to vote. So I think what's really awesome is that many of you guys are kind of like where Bonsai was a few months ago, right? Very early on their VLA journey, trying to figure out what the right stack and the right technology to use. So it's awesome to see all of that. We have a second question, and so we're gonna end this one. Thanks for everyone that participated. And it's kind of cool to see so everyone can see kind of like who else is in the room. We have a second question, which is how data is organized for robotics has also evolved. And so we're curious if you've already adapted into newer, more modern data formats in robotics. And so we're going to ask a second poll and we'll see where everyone is on their data journey. We'll run this one for just a couple seconds and then we'll get started with Omar's section. This one is multiple choice, so make sure that if you pick one, you have the option to pick a second one or a third one along the way. Awesome. Looks like it's still a lot of Parquet, but some growing trends in using MCAP. So that's super interesting. Okay, I think last time we got a little bit over close to 90 people. We're getting close to 70. So I think with that, we're just gonna end the poll here and then go to our next section. Omar, take it from here.
Perfect. Thanks, Julian. So next up, in the next hour, I want to walk you through the technical aspects of fine-tuning VLAs. I'll show you three things. First, we'll talk about the actual challenge and architecture for scaling out VLAs. Then I'll show you some code running live. And third, I'll talk about how Ray and Anyscale come together to make that accessible. So let's get started. First, what is the challenge really stepping back? The first challenge comes from a need for scale. These VLA models are already bigger than the classical perception or planning models that you've been working on. And they also open up more data for you to do the training. You can mix both externally cross-embodiment data that's available on the internet in addition to yours. And what that means is it's going to go beyond the infrastructure you currently have. So if you're a researcher, the GPUs that you have in your workstation will not be enough. Maybe the cluster that you provided is not big enough. And for platform folks, it means you need to be able to provide your researchers a lot more capacity. And the backdrop is that the robotics industry is just accelerated and energized by the VLAs. And now, just to remain current and competitive, you have to iterate faster than ever before. And because these VLAs are bigger and require more data, training runs are longer than they're used to. And third, you start bumping into resource limits. They require more GPUs, bigger GPUs, but also the limits of you as individuals, ML researchers and platform teams. And that's what is driving the need for scaling. Now, what we've seen is that folks like you who are starting their VLA journey begin to think, well, if one GPU and my CPUs are not enough, how about I try vertical scaling? What if I try going with a larger machine? So bigger GPUs or a machine with a lot more GPUs, let's say 8, which is the current maximum that cloud providers are going to give you. Now, this approach has some benefits. First of all, it's simple. You get your access to a bigger machine with bigger GPUs when you can get them, and you get speed up. So in many ways, it just works as long as you can get those machines. But does it really solve the problem? And the answer is no, it can only get you so far. First of all, we're seeing folks like Bonsai and others who, when they do that, are still not meeting the iteration speed they require. They're still seeing these runs go for multiple days. And that's because you can't scale beyond the 8 GPUs. And second, this approach will not address the data loading bottleneck. One of the things that frequently happen is as you load your data, as you have to decode videos that are larger and larger resolutions, the bottleneck becomes the data pre-processing, the normalization, the decoding of that video before you load it into the GPU. And so going to more GPUs on the same node with the same CPU GPU ratio doesn't fix that. In fact, going from 1 GPU to 8 makes the problem 8 times bigger. The bottleneck is bigger and you have more underutilized GPUs. And it doesn't address cost efficiency when it comes to that. So yes, the vertical scaling approach is going to get you to some speed up, but it's not going to really address the problem. So what you need to then think about is distributing the work. You need to find a way to get your data from the source and stream it through CPUs with that pre-processing into your GPUs, but do it in a way that independently scales the data streaming and the loading from the training so that you can get more and more CPUs doing that pre-processing so that you can then saturate the GPUs and get to maximum speed up, maximum utilization. Now, distributed computing is going to speed things up to the extent that you can scale beyond the 8 GPUs. It'll get you closer to where you want to get with iteration speed. It'll address the bottleneck with data loading because now you can scale CPUs until your GPUs are full to get to 100% or close to it, and therefore improve cost efficiency. The challenge is, as you think about distributed computing, you bump against a new issue. It really isn't simple to do distributed computing. It's complex. There are a lot of complexities. And it can feel like you're jumping out of the frying pan into a fire. You're swapping one set of challenges with a new set of challenges. Distributed computing is going to introduce 3 categories of problems. First, how do you actually distribute the computation? How do you make sure that you're sending and orchestrating your data processing to some nodes and you're training to others while making sure everything is running as close to maximum utilization as possible? And second, how do you do that without impacting the developer experience? How do you minimize code rewrites? How do you use existing tooling? You don't want to change your framework from PyTorch to something else. And how do you manage dependencies and distribute them? And for the platform folks, how do you provision those clusters, making sure that you're governing across users and teams, handling failures, provisioning clusters, and optimizing cost when it comes to those GPUs? So the risk is going to distributed computing can introduce new challenges, and a lot of folks hold back from doing that and just continue to settle for the iteration speeds that you already have. Well, in this webinar, what I want to talk to you is show you that with Ray, you can actually take Python code in a simple way using the tooling that you already have, whether it's PyTorch or Hugging Face, Python, take it through Ray to get to distribute VLA fine-tuning very quickly. So what is Ray? Ray is a library. It's a Python library. You can do pip install Ray, and you are good to go. At its core, it has some fundamental abstractions for distributing code. And then what we did was write a few libraries on top of that to make it really easy to abstract your AI workloads. And the two that I'm going to call out today are Ray Data and Ray Train. Let me show you how those come together. Now let's have a look at an example of using Ray Data and Ray Train. The idea is to get parallel data processing and loading separate from distributed training. How do you express that in Python? Well, first, you import Ray, and then you specify your data loading and pre-processing pipeline, and you express it in pipeline using Ray Data. In this example, we start with reading a Parquet dataset, which is still one of the most common formats still in use today. And then typically what you need to do is your Parquet represents an index of episodes that has references to where your videos and your action and state data is. And there's typically a step to take every episode and convert it into rows of frames. So typically you have a flat map that takes an episodes, and for every episode returns a row for every collection of frames, depending on the number of cameras that you have. Well, after you do that, there might be a couple of pre-processing steps, including normalizing your data or other pre-processing that you may choose to do as you load things into the VLA, and that may include tokenization or whatever it is your particular experiment requires you to do. So you can see in 4 or 5 lines of code, what I've done is I've specified at a high level what my pipeline looks like. That is ray data. The second part is about ray train. And what ray train does is it gives you the ability to express a few things. First, you use a trainer that matches your framework of choice. So if you're using PyTorch, then you would use a torch trainer. And then what you'd have to do to prepare is a few things. First, you'll take your training loop and adapt it in maybe 4 lines of code to be ready for ray train to distribute. You would specify the parameters that you want your training loop to take. You'd specify how you want to scale in terms of number of GPUs and some other running configuration. You pass it the data set. So that second step, step two, is about specifying how you want your training to run based on Torch. Now, I will get into details of that when I show the demo, but at a high level, that's how it works. And then, and only then, when you execute the training using a trainer fit, what Ray takes care of is the following. It sets up the entire pipeline, separating out the data streaming part, the pre-processing and the data loading, and scaling that to as many CPUs are needed to feed those GPUs. So the training code is sent over to the GPUs or the GPU nodes, and the pre-processing is sent to CPUs and CPU nodes. And all of this is going to run in your cloud, in your choice of environment, whether it's the hyperscalers, neo clouds, or even your on-prem environments. And Ray makes this possible because it connects code on the left to infrastructure on the right. Now, for many of you, you may be saying, well, Omar, you're hiding a lot of complexity here. How challenging is it going to be to express my data pipelines? How challenging is it going to be to wrap my training loop in Ray? And that's what I want to show you next. It really isn't that complex. It's well documented. And in today's demo, what I'm going to do is show you how I took an open dataset, the Droid dataset 1.0.1, and how I connect that to Physical Intelligence's Pi 0.5 VLA, and I do fine tuning. Let's have a look together, and I'll start here on my Anyscale environment. So very quickly, Anyscale is...
Omar, you're not sharing your screen yet.
Okay, let's go ahead and do that. So far I've been speaking about Ray. Ray is open source. You can get it deployed in your own environment. You can do it yourself. It's open source. What we've built in Anyscale is the best way to run Ray clusters. And so you can see that on the interface, you have access to a set of cloud environments. I'm currently on AWS, but I could be on Azure, Google, or on-prem. And what Anyscale in a nutshell is, it makes it really easy for me to spin up Ray clusters. And Ray clusters or Anyscale come in 3 flavors. Most relevant to the robotics industry are going to be jobs, which are just like they sound like, clusters that are there to run a job and then stop. They're ephemeral. And then we have workspaces, which are Ray clusters that also are development workstations. And it's really easy to do those. Let me show you how that works. I am going to create a workspace, and I'm going to do it based on a template. We actually have a template that you can begin to use and follow along as well. We'll be sharing a link to this template with a chance to get credits so you can get started for free using these. And what I'll then do is just launch a workspace based on that. And what Anyscale is going to do now is go ahead, take the time to launch on my AWS account a Ray cluster with the compute configuration I need and the code that I need as well. This will take about a minute to a minute and a half. Instead of having you all wait, what I've done is actually created a workspace already, and here is what it looks like. This is what my workspace looks like. I have the chance of connecting to it through a variety of ways. After all, it's a development workstation, but it is also a Ray cluster. And in this case, it is running a head node for Ray, some CPU nodes for CPU processing, and I pre-allocated 2 GPUs already, some L40Ss. So I have two things, a development workstation and the Ray cluster combined. Let's dive in to the actual code. Here is my connection to my workspace. This is a workspace where you too, once you launch that workspace using that template, you'll have access to all this code. And to give you a quick tour, the main part of the code is this notebook called VLA, and it references code in the subdirectory where I have my data preprocessing code, my training code wrapped in Ray, and some code to compute statistics from the data set for the purpose of normalization. Let's go through this together. The first step that you will face is some setup, and that includes installing your dependencies, adding your Hugging Face token. Turns out that Pi 0.5 requires access to Hugging Face in order to pull the VLM, the backbone, which is PaliGemma. So that's going to be a prerequisite. And once I have my token in there, I run some initial code to initialize Ray. Let's do that together. And in a few moments, what I'll find is that my Ray cluster is running. It is based on a specific version of Python and a specific version of Ray. Now, as I go through this exercise, I've pre-populated some constants. I have, for example, a path to my episode index. This is basically a Parquet file that lists my episodes and passes URI, it includes URIs to where my action and state data is. And then for every episode, there is a one-to mapping to an MP4 for every camera. If you're familiar with the Droid data set, there are typically 3 cameras, and so every episode has 3 MP4 files. And I specify my accelerator is going to be an L40S for the purpose of this, and I point to where my data set exists. The Droid data set, I made a copy. Now, working with data typically requires a normalization step. I pre-computed these. You can look at the code later, but it is going to be what you expect it to do. I run through the data set before training and get statistics around so that I can later use that to normalize. So standard deviation and mean. Now let's look at the data set pipeline itself. The goal is to read the data, decode the frames, the videos, and create the frames, connect them to the action and state, and then do some pre-processing before on GPU nodes doing the actual fine-tuning. And I start with the data set first. So here I import Ray, and from my own library, I import the functions for taking an episode and converting it to rows ready for training, some pre-processing as well, and I think that is sufficient for this case. There is a utility function that I use to make sure that the paths associated with episodes are clean. I define my pipeline as reading from S3. For this demo, I limit the number of episodes to just a few, just because I don't want to launch a large-scale job. I clean up the URIs, and then I convert every episode to a set of training rows before running the pre-processing. I use Ray Data's lazy evaluation and streaming constructs to specify the pipeline and get it planned without actually executing it. And so when I specify my pipeline, it takes about a second. Nothing has happened except the planning of the pipeline at a high level. The next step is the second half, specifying the training. And here I'll go into a little bit of detail. The RayTrain library provides a few concepts that include a scaling config, where you specify how you want to scale your VLA fine-tuning, a running config in which you pass parameters around the run itself, and a failure config around how you want to deal with failures along the way. And it provides utility functions for the training. The other thing I import is a training loop per worker function that I wrote, and I will be showing you in a bit. And to be more accurate, my colleague Ian has wrote that function. All right, let's dive into each of these concepts. My scaling config in this case is 2 workers, where each worker is going to use a GPU. And if I want to, I can specify the accelerator. If not, it'll just use whatever GPUs that it has. A running config is going to provide things like a name for the run, a path where we can put checkpoints, and how to deal with failure config. There are a lot of parameters that you can tune when you specify your running config. And then I think about the training loop itself, every worker, what config information it has. This includes hyperparameters like the learning rate, the batch size, number of epochs, etc., as well as other parameters. Now, when I have these all configured, what you do is with RayTrain, you initialize a torch trainer, specify the training loop, its config, how you want to scale the running config, and pass it the data sets as a parameter before you actually run the training fit. This template of specifying the data pipeline, the data loading pipeline, followed by the trainer, is quite standard. And it is the way where you can get to scale beyond a single node, scaling up to not just 8 GPUs, but 16, 32, 128, and beyond. Now, as this gets started, one of the things you'll notice is it starts by processing some dependencies. And what's happening is Ray is taking care of spinning up workers on the GPU nodes and using UV to deploy any dependencies. Now, because this is my second run, this is almost instant. The training begins and it begins to execute. What I will show you next is 2 things. First, I'll go back to the web portal and show you the metrics and the observability that we provide. As you run this workspace, or whether you're running a job, you're going to see all sorts of metrics and logs, including things like infrastructure, the count of nodes, the hardware utilization, the CPU usage, memory, etc., and GPU usage. At this stage, nothing has started yet. And you can go down to the specifics of actually for a training run, what is happening for the data processing, specifically what is happening. And if we dive a little bit deeper, we now see that in a prior run, this is how the Ray data pipeline has processed. There's the input, listing all the files, reading them, taking them through the pre-processing and reading. You can watch these and actually see them in a DAG view, in addition to training runs. There is one that I aborted before, but there is now the training run that is currently running. You can watch logs, see the metrics, controllers, etc. As you can see, there are 2 trainers already running. I can do profiling and really understand capacity. So we don't only provide in Anyscale the rate tooling, but we also provide the uh, the developer experience around it. Now, conscious of time, what I'll do is show you as this training is running, what I did or what Ian did in order to take existing code and wrap it in rate train. And specifically, I'll take you through the code available in the code for train worker and take you down to the training loop specifically. Here on the right is the training loop per worker. This code is primarily adapted from the OpenPy repo. So this starts with code that was provided by Physical Intelligence themselves. And we make 4 changes to the code. The first change we make is wrap the model in DDP. And the idea is the architecture that I've shown so far is about distributing training across multiple workers and doing DDP-based training or distribution. And doing that is as simple as calling this ray train utility function prepare model with the policy as downloaded, in this case, from the robot. That is change number 1 to your training loop. As you can see, the rest is going to be things like forward pass and so on. But before that, the second change that you will have to do is Ray data is going to stream the data, but it's going to stream it because it's data parallel into shards. So the second thing that you do is you will use your data, you will get a data shard, and that will represent your data loading. That would be the second change. And the third change would be using that shard, data shard, iterating using this utility function, iter torch batches. What this is going to give you is a set of batches that you can then take through the loop. So a forward pass, a backward pass, this is all standard. And fourth, you make a change by actually running a checkpointing every certain number of steps, and RayTrain has some capabilities for doing that. And so what I hope I've shown you in the last 2 minutes going through this code is there is a finite list, in this case, 4 changes you make, and you can take any open source repo or even your own training code, wrap it in RayTrain, so that then you can go back and do this, pass that training loop back to the worker. The same concept applies to the data processing workloads that you have. So just to summarize then, what I hope that I've shown you so far is that you can take code like this, express it in Python, and get automatically to this architecture independent scaling of streaming and training across CPU and GPU nodes, wherever you want to run your scaling, to get to 100% utilization with the limited resources you have, which is your time and the underlying infrastructure. That wraps it for the demo. Now, there was a question, how much time are we going to spend on Ray, and are we going to talk about Anyscale? Well, so far we've been talking about Ray. I do want to wrap by talking about what Anyscale adds in addition to Ray. Ray is open source. You can download it as a researcher and code in it. As a platform team, you can build Ray clusters and manage them yourself. Anyscale takes Ray, optimizes it, and as that layer we call the Anyscale runtime. So we have a version of Ray that performs just a little bit better, that has certain capabilities that are not open source. We add Developer Central. I gave you a taste of that, which is just workspaces and observability. I showed you the kind of graphs that you can see and how you can spin up array cluster so that you can start developing. And in the southbound way, to interact with the cloud, making it really easy for platform teams, we have the cluster controller that orchestrates the infrastructure with monitoring, governance, and budgets. So Anyscale takes Ray and makes it easy to use so that you get efficiency for developers, ML researchers, as well as platform teams. Now, with that, I'll hand it back to you, Julian, to moderate Q&A.
Yeah, I think let's go to the next slide and just leave that in the background as we go through Q&A. So the resource that was shared. Oh, Omar, do you mind sharing the screen? Yeah. So the we shared on the chat the demo, so you guys can go play with that. All it takes is signing up to an Anyscale account to be able to do that, so you don't have to worry about the cluster management and all that kind of stuff. We do have recently Omar wrote a blog on VLA, so definitely check that out. And then if any of you are coming to NVIDIA GTC in maybe a little bit over a week, we're hosting an event there, a happy hour with weights and biases. So would definitely love to meet some of you guys in the real world. Now, with that in mind, yeah, let's go through some Q&A. And I'm gonna start maybe kind of thinking from the top. One of the questions that came in that I think will be good for everyone to hear is, what is when I install Ray, am I getting Ray core, Ray data? What's the difference between kind of like the core versus the libraries when installing that?
So I'll take that. And so Ray, when you pip install Ray, you get all the libraries and you can be selective. So you can pip install Ray data or Ray train. It's open source, so you get the full setup. That is what a developer would use to set things up. The other side of the story is you need an environment where you can deploy Ray clusters and so on. And so the platform team, your platform team, has to do some work for you in order to go from your laptop or your development station to production. Anyscale is one way to do that. Some platform teams may choose to do it themselves. We are the best way to do it, and you would see if you give it a try. Let us
Makes
know
sense.
if that answers your question or if you have a follow-up.
No, I think it's the sometimes how I like to summarize it is like you kind of get everything, but just know that the libraries, data, trainer, abstractions on top of Ray core. So you can always use the abstraction or you can go all the way down and implement everything in Ray core. I think it's another one that very common, and especially those that come from academia. What's the difference between Ray and Slurm? What would be kind of like your answer to that, Omar?
So Ray does a few things that Slurm does not, and likewise for Slurm. What Ray does is it allows you to express in Python how you want to distribute your code across CPUs and GPUs. So within Python, you're able to express your pipelines and how you distribute them. What Tree then does is it manages the communication for you. So if your data workers need to communicate with the GPU training workers, you don't need to actually think about that because of the abstraction. And second, Ray does a great job managing heterogeneous compute. And VLA fine-tuning is heterogeneous because you need a lot of CPU processing and a lot of GPU processing, and you want to do that on the fly with auto scaling because you don't know how one additional pre-processing step is going to impact the ratio of GPUs to CPUs. So Ray is going to do that dynamically with auto scaling and so on. And there are a few other changes. I mean, there are places where Slurm really works. It's come from an HPC, homogeneous computing backdrop, and it is widely used. Ray is surpassing that for AI workloads increasingly.
No, I think that's a great answer. Here's another one that may be good to clarify. what is the role of something like PyTorch FSDP versus Ray, and how do I think about those two together?
So they are not exclusive of each other. So you can combine both of them. The topic is probably beyond the scope today, but just keep in mind that you can work both of them. We actually have templates on Anyscale where you combine ray train with FSDP and get them to work together. They work at different layers, and it's a common use case to combine them. Again, the ray train approach is about working with whatever tooling you're using in order to do that. What I can do is, as we take more questions, point you to a template that you can look up when looking at that in more detail.
That'll be awesome. And then kind of I'm seeing another question that I think maybe we always assume it's common knowledge, but why is it that there's an 8 GPU limit? You kind of mentioned this at the beginning. You can go from 1 to 8, but why is it that I am limited to 8 when I do vertical scaling?
Um, good question. It's just that as you go to vertical scaling, if you want a node with more GPUs, cloud providers don't give more than 8 GPUs in one node, right? So you get 8 into H100 or 8 into A100 and so on. So there's a limit how big these nodes actually get and become available. So if you're vertically scaling, that's the limit. In the future, there may be nodes that have more GPUs. Maybe there are currently, but that's the simple reason. Now, if you want to get to 128 nodes because you want to speed up your training and you want to get results a lot quicker, you're not going to get a single node that has that. And so you have to think about distributing training then.
Yeah, I think I have another one that's going to be maybe not easy to overgeneralize, but the question goes, I've added a few CPU only nodes to my heterogeneous cluster to handle the data loading and preprocessing. And so, what are your recommendations to optimize the data transfer between the data loading nodes and the GPU-based worker nodes?
Um, so there are going to be a few considerations. First of all, you have to begin by trying to think about the ratio of CPU nodes to GPU nodes. And that can be challenging without a framework like Ray. Because first, it's hard to understand how much processing, it's a bit of trial and error. And second, by the nature of experimentation, you're going to be introducing new steps along the way. And so if you get to a ratio, it's going to change as you experiment. And so what you want to do is make sure that you have auto scaling. So you have a good guess to the number of CPU nodes you need, but allow room to scaling. And typically what I do is I take a guess and then I have auto scaling from a little less than that to double the amount. And that allows me the ability to efficiently scale out. Second, what you can do in some use cases, if you feel like you may be IO network bottlenecked, what you can do is think about your choice of CPU nodes and the networking underlying them. So if you have your cloud provider has networking optimized nodes, you can choose those over the others. If the preprocessing is CPU bound, then you could choose. And so that is a second way to do that. And by the combination of scaling, auto scaling the CPUs and being selective about them, you can fairly easily get to saturation. If that answers your question, great. If not, feel free to type in a follow-up.
Awesome. Yeah, Florian, let us know if you have any other questions. I think here's one that I think it's worth acknowledging, and then kind of I can share some insights on that. But is the NVIDIA NVL72? That one has more than 8 GPUs, and so what does that mean in terms of vertical scaling?
Well, and the number is going to increase over time. So, if it gets you past 8, then good. For the vast majority, they may not have access to that. And that is why I mentioned the eight GPU. And I appreciate you sharing.
Yeah. No, and I think for you guys that are thinking about that, one is yeah, not everyone is gonna have access to the 72 racks on a single or 72 GPUs on a single rack. But if you do, you're gonna run into a different set of challenges. And so we're gonna be making some announcements at GTC of how we're working with some of the large AI labs to get the most right. Because now you're gonna be thinking about how do I know that this GPU is close to the other one, and how do I optimize how things get communicated with each other? And so vertical scaling does not make things easier nor faster if you don't have the right orchestration handling your multi-step heterogeneous workloads. Let's see if Florian added anything else. No, I think we're good. Florian says, great answer, and thanks, Omar. We've answered a lot of the other questions, Ian. Thank you so much for helping answer questions along the way so that Omar could get us through the full presentation. Like we said, please check out the fine-tuning resource. If you're going to be on site at GTC, definitely come hang out with us at the happy hour. And for now, if there's any other questions, feel free to reach out. We're going to be sending the recording. We're going to be sending the link to the fine-tuning demo as well. And then along the way, again, if you have questions on your VLA journey, reach out. Thanks, Omar, for the time and putting all of this
So
together.
I do actually want to tackle
Mm.
two more questions and
Oh,
add
go
some
for it.
color. I know, thanks, Julian. So there was a question about best practices around scaling massively. So obviously, the focus of this webinar is getting started on the distributed journey. Uh, and specifically, there was a question about GCS becoming a bottleneck.
Mm.
In the world of Ray, GCS could mean two things. It could be Google Cloud Storage or the internal Ray component that is called GCS. Uh, if this is a matter of Google Cloud Storage becoming the bottleneck, there are some best practices about how you lay out your data in order to make sure that that is not the case. If the problem is about scaling Gray itself and it becoming the problem, let's talk. We have a few optimization for the version of Ray we run on the runtime, which has a bigger scaling envelope, and our engineering team will work with you to work through those. We've seen many customers who felt that there were bottlenecks related to Ray, but through changes in code and architecture, we've managed to get them passed through that. We're happy to share that. And the last question I'll take is there a preferred data format for VLA? We don't have a preferred framework. The ones we've listed are what we're seeing. HDF5 has a legacy, so does Parquet. We've seen a transition to MCAP, particularly for AV companies. And because of MCAP's integration with ROS, we in Ray have Ray data read MCAP, so you can read directly from MCAP files. But we're also seeing increased demand for the LeRobot data set. In fact, with LeRobot, we're seeing demand for not being able to read just one LeRobot data set, but to pull from many of these data sets, both public and private, to combine them into one data set abstraction. Stay tuned. We're going to be releasing a LeRobot data source for Ray data, so that's natively integrated, and we'll keep you posted about that. In a nutshell, we'll work with your data set. You'll be able to tweak it. It's Python under the hood with some Ray abstractions on top. And so with that, back to you, Julian, to close.
No, I think thanks for taking those additional two. I think we're starting to see people jump off. And so, not going to repeat myself. Thanks everyone for joining. And if you have any questions, feel free to reach out. Have a good one, everyone.